In this section, we're going to talk about a specific type of sequence, monotone sequence. A sequence is increasing if the first term is smaller than or equal to the second term, smaller than or equal to the third term, and so forth. It is decreasing if the inequalities are reversed. The first term greater than or equal to the second term, which is itself greater than or equal to the third term, and so forth. A sequence which is either increasing or decreasing is said to be monotone. Be careful here, when we say either increasing or decreasing, we mean that it is increasing in its entirety or decreasing in its entirety. It could be one or the other. It doesn't mean that it is sometimes increasing and sometimes decreasing. If the sequence is both increasing and decreasing, then we say that it is constant. Increasing sequences play a role similar to the role played by increasing functions. Decreasing sequences play a role similar to that played by decreasing functions, and obviously constant sequences play a role similar to the role played by constant functions. The main result we have for monotone sequence is actually quite useful, and that result, combined with the nested intervals theorem, is going to allow us to prove a very important result from the analysis of sequences, in particular bounded sequences, the Bolzano-Weierstrass theorem, which is a topic of the next section. Assume you have an increasing sequence xn. Assume further that it is bounded. And because we're talking about an increasing sequence, the boundedness that really matters to us is the bounded above part. So this is going to be a result that's going to be true for bounded sequences in general, but it's the fact that it's bounded above that's going to be used. So I'm going to specify here that it has to be bounded above. I don't really need to specify it, and you'll see why. If the sequence is increasing, I don't really care what happens below the bound, but let me just still specify. If, as I said, the sequence is bounded above, then it is convergent. We can say more. Not only is it convergent, it also converges to the supremum of the values the sequence. Before we do the proof, let's think about what this means for a second. Consider the following sequence: 1, 2, 3, 4, 5, 6, and so forth. This is the sequence xn equals n. This is definitely an increasing sequence, but it is not bounded above. There is no number x which is greater than all of those numbers. I've seen it when we looked at the proof of the Archimedean property of the real numbers. And so, well, actually nothing. We can't apply the theorem. This is not a convergent sequence, even though it is increasing. So you see that the boundedness part actually matters. Now some of you might say, well, hang on. Can't I just say that the xn converges to infinity? Well, we don't converge to infinity. That's really the definition of a divergent sequence. What about this other sequence here? What does it look like? If you start at n equals 1, you get a 0. For n equals 2, you get 1 minus 1/2, which is 1/2. For n equals 3, you get 1 minus 1/3, which is 2/3. For n equals 4, you get 1 minus 1/4, which is 3/4, and so forth. So this is a sequence which is increasing. It's not too difficult to show because for every n, the nth term of the sequence is smaller than the n plus 1 term of the sequence. Indeed, you know that n is smaller than or equal to n plus 1, which means that 1 over n plus 1 is smaller than or equal to 1 over n. I multiply by minus 1. I have to reverse the inequality, or in this case, switch the terms. And if I add 1 to both of these, I get the following. So this is going to be true for all n, so I know that the sequence is increasing. So this is an increasing sequence. It is definitely bounded as a sequence. All of the values of this sequence lie between 0 and 1. You can be generous and say that it's smaller than or equal to 1 as well, if you want to. may be a little easier to prove. All you really need to show here, given that all of these numbers are positive, is that 1 minus 1 over n is always smaller than or equal to 1. And you know that this is true because 1 over n is always greater than 0. So you're always subtracting something greater than 0 from 1. It's got to be smaller than 1. So this is both increasing and bounded, and by the theorem, which we have not yet proven, this limit converges. If we look at it here, we have a pretty good clue as to what the limit should be. All of these values are getting closer and closer to 1, right? The limit of 1 over 1 minus n would be 1 minus the limit n goes to infinity of 1 over n, in order to be 0, 1. So it's at least sensible that an increasing bounded sequence would converge. And here, in this specific example, we're able to find what the value of the limit is. Is that indeed the supremum of the values of the set? For the supremum, you're looking for the smallest possible upper bound of the values of the sequence. I'm looking for the supremum of 1 minus 1 over n. We know, as we've seen before, that 1 is an upper bound of 1 minus 1 over n. Let's say that it isn't the smallest one. Let's call it, I don't know, eta star. Let's say that eta star is a smaller upper bound of all the values 1 minus 1 over n. Now, if eta star is strictly smaller than 1, on the one hand is that eta star is supposed to be greater than 1 minus 1 over n for every n, but it's also supposed to be strictly smaller than 1. Do you see why that might be a problem? I claim that this cannot possibly be the case. Why? Well, we're going to find a k integer such that 1 is greater than 1 minus 1 over k, greater than eta star. How do we find this one? Well, if eta star is not equal to 1, 1 minus eta star is positive, and it is apparently greater than 1 over k.